and then you take the IOU score, which is intersection over union.
It's not really each pixel, it's the overall image itself, right? So
That was used as a black box.
so
Are you predicting bounding boxes?
yes, well, yes. So if you go back to the classification, wait, no. Okay, so with this model, there's like.
I understand that.
Oh, okay.
Yeah. The question is, if you're creating bounding boxes,
Right.
you can do intersection over union. If anything else is in there, please go ahead. If you're
Sorry, are you asking intersection over union?
yes. So if you're predicting bounding boxes in
Yes.
the process, and even if it's object detection and you take the majority class, right? Your model will predict a bounding box, and your ground truth will have certain bounding box.
Oh, right. So what we actually did is the data model uses a bipartite match loss. So basically what happens is, so the data transformer itself has like a list of classes. It's kind of hard to explain without a photo, but I'll try to explain.
Okay, so that was a black box. That's the answer.
Oh, sorry. If you say so.
No,
I'm not sure if it's a black box or not.
A black box in the sense, right, from
Yeah.
your perspective as a model user or in your research, it's a black box because you cannot change that part of it.
Yes. Sorry about that.
Two questions, if we have the time. First of all, awesome presentation. Excellent book with the threads. Through the presentation, there's a lot of emphasis on making it run fast. So I was just curious, you're showing a lot of metrics into precision and accuracy. Did you guys do any performance metrics into real-time inference?
No, we didn't get to that mainly because we didn't have enough time. So we just decided to take a real-world aspect approach on that because getting a higher accuracy when detecting a disease is much more important than. Well, it's also equally important to getting it quickly, but given the time we had, we just focused on that.
That makes sense. I was curious. You guys had a lot of issues with class representations. I was wondering if you guys did any other data augmentation approaches that you didn't talk about in the presentation?
Well,
or at least attempted.
Yeah, we only did those 3 augmentations because any other augmentation would make sense, I think.
Okay, so we did try to do that. So the first initial data augmentation, they did triple our data set at first, but we also had an experiment augmentation where we put all 3 together. But that really messed up the model because it's too much. If you look at it, the rotation along with the random crop would make it look like it's not even a lung at that point. So sometimes the model wouldn't work, so we just ditched that idea. But we were attempting that at first.
Okay, I have a quick last question here. So one thing is, I know you discussed precision and recall, but in that, right, because of your problem domain, do you focus on minimizing false negative rates? Because a false positive is okay, you can get a second way to diagnose it, but a false negative can be potentially harmful.
Yeah, absolutely. So how we combated that is we actually added images, just normal images of no diseases whatsoever. And by doing that, if it detected no disease, then that counts as a false positive, right? And if it detects a disease, then that counts as a false negative. Wait, hang on. Sorry, I think you're a little confusing. Just give me a second. Okay, so you got a normal image, and let's just say that. Okay, so you got an image with a disease, right? And let's just say it doesn't detect anything. That's definitely a false negative, right? And then as far as the false positive aspect goes, if it detects a disease from a normal image, then that counts as a false positive.
Yes.
So yeah, that's how we were able to do all that.
Okay, so did you have okay, anyway.
Okay.
Oh yeah, we can answer your questions after
Yeah.
if you like.
All right, give a round of applause for that. Thank you so much, guys. So
Wait, what if
Hey guys, we're starting the next presentation, so I would really appreciate it if you would not huddle up around there for the pizza. Thank you. Yeah, okay.
So hello everyone. Our research is bare metal programming an embedded system to compute paths in 3D space. I'm Ras Thapa.
I'm Pranay Lakarajan.
I'm Omar Abioye.
And I'm Michael. And we are missing a faculty advisor. Apparently he went to get the milk and he hasn't been back yet. So we hope to see him eventually. Hope not tonight.
And our lead is Adit. So before in-depth discussion about our research project, I just want to talk about some of the topics that are really important in this research. So the first topic is embedded systems. So embedded systems are computer systems designed to perform specific tasks. They are reliable, they are cost-effective and efficient. Embedded systems are also used in a variety of applications, including consumer electronics, automotive, aerospace, medical devices, and industrial automations. But developing embedded systems are always challenging because, due to the limited resource available on the hardware platform, the need for real-time performance, and the need for reliable operations in harsh environment. The next topic is fixed points. So fixed point notation is a method of representing numbers with fixed number of binary digits for integers and fractional parts. They are used in embedded systems because they are more efficient than floating points. They are also useful for high-speed computation with limited resources. They can represent both positive and negative numbers in formats such as cube format, Q's complements, and sign magnitude format. Also, fixed-point arithmetics are performed using shift operations. And also, it is important to choose appropriate number of bits to avoid errors such as overflow, underflow, and quantization errors.
So in our project, we use what are called Bezier curves. Bezier curves are a type of parametric curve that is defined by a couple of control points that decide the shape of the Bezier curve. So there are multiple types of Bezier curves depending on the amount of control points that define Bezier curves. So linear Bezier curves are defined by 2 control points, quadratic Bezier curves are defined by 3, and cubic Bezier curves are defined by 4. So one thing that's special about Bezier curves is they are defined mathematically. And they have other applications too, like in typography and computer design, animation, modeling. In typography, since these curves are defined mathematically, we can scale into them, like if they tested them, and we won't lose any information from end results. So they can be used to create our letters A, B, C on a computer. Also, in terms of computer in modeling, we can use Bezier curves to create smooth paths for objects to travel with, or we can use them to represent models.
So why are we doing this, and what are we doing? So embedded systems typically are not good at and not capable to do heavy computations, such as Bezier. to calculate Bezier curves and polynomial integration, polynomial interpolation and integration and such. So what we sought out to do was use fixed point notation to allow these embedded systems to do these calculations with little error, there's some, and use less energy and need less computational ability. So applications. So one application would be UAVs. You know, Bezier curves are useful for pathing in general. Another would be robotic synchronization. Typically, industrial robots, you want them to move in a curve, not straight angles, as to prevent them from their gears from being ruined over time, gives them more life. And real-time motion evaluation. It allows, well, typically you want a curve with your motion. Typically, motion is defined by a curve. So if there's sharp deviations within this curve, you know to signal to some safety system or something to initiate some type of safety system.
So in order to make our project work, we have designed or created a bunch of functions, a bunch of tools. And one I would like to bring your attention to is what we call the Gaussian quadrature. What this does is it finds the integration of, well, our Bezier curves. We use it to approximate integration. And we can use that integration to calculate the arc length of our curve, which is quite important depending on the application you want to use the curve for. We also have what is called a Bernstein polynomial. The Bernstein polynomial is a sort of representation for, well, polynomials. And they are particularly useful in Bezier curves in that we can use Bernstein polynomials to calculate the position of a hypothetical point on the curve given some time t. You can find the position of that point, the acceleration, velocity, and other useful metrics depending on our application. Next one.
So the significance of this data is just that there's very little error, and it was able to be calculated in only 30 to 40 microseconds on an embedded device. So hypothetically, we could use an embedded device with even less computational capabilities, which would reduce cost and other metrics that are important when designing something.
So our solution works, but we definitely had some drawbacks getting to this point. And in terms of the testing phase drawbacks, we showed a visualization of the Bezier curve on a 2D plane, but we ran it on a Raspberry Pi Pico. Unfortunately, some of the libraries, when we were compiling it for the GPIO pins, didn't connect correctly. So but it works now. In terms of development, we had an uninitialized variable in the for loop, which caused it to output the incorrect values. So in the for loop, in that top code snippet there, we looped it until 4, but we changed it to 3 and it started working. So in conclusion, we have successfully been able to do Bezier mathematics using fixed point notation on an embedded device. This allows us to calculate computationally intensive workloads on very cheap computer processors to the most expensive computer processors. And like we mentioned about the applications of
drones, automated system, autonomous vehicles, and wearable devices. We have demonstrated a way that you can run a high level of computing workloads on small devices. Thank you.
Awesome presentation, guys. Just a couple questions. I wanted to ask, did you guys compare essentially like your model architecture and your approach to any other state-of-the-art architectures within the field? And sort of a second portion of that question is, how did you tackle exploring those similar approaches as a team?
No, we did not do any comparisons. We did not have the time, unfortunately. We kind of ran out of time at the end. But as for figuring out how to do most of this stuff, it was mostly just the internet. And our group leader was very useful in helping us.
I'd like to answer that question. We have to also consider the architecture we're working with. So, for example, we were using fixed point numbers, and, well, industry standards, they use floating points. So, for the most part, we were heading in blind, trying to figure out what we could learn from our research projects. So, no, we didn't want to compare results with industry standard.
And one other question. You guys were serving this on a Raspberry Pi. What were some approaches you took as a team, like to get that to work? Was there any complications in quantization or just serving in general?
Well, specifically, it was the Raspberry Pi Pico. And yeah, there were a couple complications with specifically something Pranay said earlier about that one uninitialized variable. It took 4 days to figure out where exactly it was going wrong, because on Audit's laptop, it was running completely fine, but when we uploaded it to the Pi Pico, random numbers, and we had no idea.
That's C for you. Okay, I want to thank you for judging us. I want to thank you all for listening to our presentation.
Thank you. So our next presentation will be the Taming the Tornado team.
Hi, I'm Sachin.
I'm Victoria.
We gotta introduce the project, right? Well, I just think.
Okay, sure. Yeah. I'm Reed. Nice to meet you all.
I'm Des Contram.
And our project is handling the tornado money laundering detection on tornado cash. So first off, I would like to thank our faculty professor, Dr. Kontarsioglu, and our research lead, Rohan, who have both provided us with valuable support and guidance throughout this semester. 455 million US dollars. That's how much money North Korea stole by abusing a protocol called tornado cash. But to fully understand how North Korea and many others pulled off such a feat, we have to first understand a few key terminologies. First off, blockchain. Blockchain is a secure and decentralized method of record keeping. Now, there are many complicated terms that we need to understand for how it works, but the main concept here is that blockchain can be used to make transactions and store data. So it's completely immutable. So once you add some data onto the chain, you can't change it, and it's decentralized, which means you can make transactions from peer-to-peer without any intermediary to verify the transaction. And lastly, and probably most importantly for this project, the blockchain is completely public, which means that anyone can see any of the transactions on the blockchain. Now, this can be helpful in some cases where the transactions need to be public and transparent, but for many individuals and organizations, this is a serious privacy concern since all their transaction data is basically publicly exposed. We need a better solution. Introducing Tornado Cash. Tornado Cash seeks to solve this problem by allowing users to make transactions anonymously. So how it works is you first deposit some Ethereum into a large pool with other deposits of Ethereum from other users. Then you get a secret node. So the user gets a secret node which he can use to make a withdrawal. That's completely separate to the original deposit. So unfortunately, this system became really good at making anonymous transactions that criminal imposters were able to use the anonymity of the transactions to launder money. So after large sums of money were laundered from both North Korea and many other sources, the US government eventually banned this protocol.
What our group sought to do was propose a methodology by which a government authority would better be able to detect and combat these money laundering attempts. Specifically, in order to do this, we created a tornado cash protocol simulation of our own in order to kind of modify it, see what's going on and stuff like that. In our simulation, there are two types of user entities. The first one being the government entity. What the government entity seeks to do is to, I should slow down the words. What the government entity seeks to do is to deposit a large amount of ETH into the pool to gain a certain percentage control of what is deposited in the pool at the time. This is to artificially inflate the anonymity of the Tornado Cash application, as well as confuse linkability heuristics. The second type of user is just a user entity. I said user entity, it's a user entity. But what user entity does is it's just a normal person. They make deposits and withdrawals within the simulation, and it's just meant to represent an average user or potential money launderers within our simulation. How we made our simulation is we took the publicly available Tornado Cash contract code, which is still up, by the way, and what we did was we modified it and we launched it on a Ganache instance, which is a local representation of a blockchain. Our goal in this was to see what effect modifying the percentage control of the government entities, the control of the pool, would have on the overall address linkability. In order to do this, we ran multiple simulations with the numerous different number of transactions. The first was that government entities would deposit large amounts of ETH based on the desired pool percentage. So so we had 100 set users, but in order to get a desired percentage, we had to calculate the number of government transactions needed in order to confuse and inflate the anonymity pool. Well, instead, user transactions would be randomly, 100 random user deposits would be randomly distributed within the time frame of 1 day, and then within a couple hours later would randomly make a withdrawal concurrently with government transactions. With all this data at varying percentages, we were able to collect a few points of interest, namely the transaction time of each deposit withdrawal, the address that was linked to it, and the gas cost, which is essentially just a fee for performing block mining and for performing transactions on the blockchain. It's important to note as well that in the simulation we're only representing the government authority as one actual address, when in actuality this can be performed with many addresses to hide that it's just one address doing this, while there are many users. With all of this data we collected, we went on to the analysis stage of our research.
So this is the graph of our results. As you can see on the x-axis, we have the percentage of the Tornado Cash pool that is controlled by the government account. On the y-axis, we have the accuracy rate of the heuristic we use to link addresses. And so the blue line is the analysis performed from the perspective of a normal user who has no idea what's going on with the government deposits. And the red line is the government analysis. So as you can see, the government analysis has a higher or equal accuracy rate to the user analysis for all data points. And this makes sense because the government has access to the fake deposits they're performing, whereas the user has no idea that this is going on. Another interesting thing about our results is that there's no consistent increasing or decreasing pattern with increasing government control. This was unexpected, and it's because instead of basing our simulation on actual user data, which is really hard to obtain, we based it on random patterns, so that led to some random fluctuation in our results. But despite this randomness, we're still able to show that the government has higher accuracy due to being able to exclude some data points in their analysis.
So similar to our previous graph, we have the x-axis that represent the government pool controls. This time, the y-axis represents the amount that the government must spend in the gas fee should they try to get a higher percentage of the pool. So this graph shows an exponential relation in that the government must spend an increasing amount of money in gas fee should they try to achieve higher percentage of the pool, which is not entirely unexpected. It just spell harder deployment should they try to get it on a larger scale.
So after doing all this data collection and performing all this analysis, why is this meaningful in the real world? For two reasons. So the first reason is that the Tornado Cash contracts are publicly available. The code is in a public GitHub repository, and as a matter of fact, a lot of similar coin mixers are actually still publicly available. The second reason is that blockchain is decentralized, so even though the government can sanction Tornado Cash, there's no way for them to prohibit individual users from still interacting with the contract even now. So it's impossible for the government to just ban Tornado Cash, so they need to find some alternate solutions, which leads to the need for further research, which can be based on the methodology we outlined here today. Thank you for listening.
I have a couple questions. The first one is, what is linkability heuristic? So from the chart, I feel it's the percentage of users you've identified, but is there a better definition for that?
Yeah, so what we did with the linkability heuristic is we did some literature review, right? And so we ended up, I think we attached the study that we had in our poster, but so the linkability is, so we looked at like deposits and withdrawals. Obviously we ran the simulation randomly, but so for each deposit, we looked if there was like a falling withdrawal within 3 minutes of the deposit. So the way Tornado Cash works, right, is it's every deposit's anonymous and every withdrawal is anonymous. So any transaction, a deposit and withdrawal that's happening within close proximity to each other is automatically suspicious. And we also checked how much each deposit and withdrawal was. And again, if they were of similar amounts or same amounts, it's also suspicious. So that's kind of how we developed the heuristic. And so the graph here is just like, this is just showing that it's just a relation between how accurate our heuristic was as the government had more control of the pool.
Thank you. And the second question was, how did you counter the randomness of the data? So you mentioned, right, that the results from graded are not as you'd expect because of the randomness. Did you try to counter it in some way?
Unfortunately, we did not have time to counter it. The actual nature of tornado cache is that real-world data is anonymized. It's all the actual anonymity of tornado cache comes from Z-search, which is zero knowledge proof arguments of knowledge, and so you kind of need heuristics to develop a heuristic on that. What we would like to do further is analyze alternative and maybe similar user behavior patterns in order to develop heuristics and use different literature review heuristics on that.
Thank you. If to make a small suggestion, I would say doing multiple runs where it's random seeds and averaging over them would give you a better picture. It would not be close to the usage pattern, but it would still give you a better random picture. Thank you.
Thank you.
Thank you. So our next team will be the hate deception team.
Okay, you ready for your exciting intro?
You're way too excited, dude. No, trust. You really are.
You want to say
Alright, it's gonna be
say this is
There we go.
yeah, thank you.
That's not me.
I don't think we do that.
Okay. It comes down. I can't.
Okay, we'll start now.
Say the whole lot.
So, begin?
Say hello.
Okay, hello, begin. I hate those kimchi-eating, dog-munching Koreans. Okay, no, I'm just kidding. I'm Korean, trust me on that. I'm also not racist, but that was an example of a hate speech. And obviously, that could possibly be seen as a tweet, but obviously there's countless amounts of hate speech out there. So that was the idea behind our project, Hate Deception, where we'll be using adversarial learning to deceive hate detection models for Twitter. So this is our team. Next slide. On the top is our teammates, and then the bottom we have our lead, and then our three wonderful professors who were a bunch of help for us for this project.
The rise of social media has led to an increase in hate speech, which is a major concern for all social media platforms, especially Twitter. Modern-day efforts to limit this have included policies, regulations, and restrictions, but it still remains a common and ongoing challenge today.
The most common way today that you actually see companies try and target hate speech to try and get rid of it on their platforms is going to be AI language models. These models are specifically trained to detect hate speech, but hackers and adversaries can train their own models that will go against it and try and deceive it. Our project simulates this real-world scenario by splitting our group into two sections, attack and defense. And this is really important because these companies base their business on this, and having hate speech is a detriment to advertisers, and it really does harm the people on the sites as well.
Our data set includes real, academically annotated tweets that include a lot of hate speech, and we found that on Kaggle.
Okay, so for a defense system, obviously our goal was to be able to detect hate speech tweets. The methods we used was a linear passive-aggressive classifier. We also used a random forest classifier, and then we used a neural network multi-level perceptron classifier. But when we're optimizing our models, we noticed that in our data set there was an unbalanced data set. So we used undersampling to help kind of fix that. And then we also removed stop words using NLTK, and then we used a library called GridSearch CV to help change parameters for our models that will run through different combinations of parameters that will help us with the best accuracy we can. So for our performance, we measured it based on how accurate the models could detect the hate speech. And so just a quick rundown of these models. Now how the passive-aggressive classifier works is that in the passive sense, the model will make a prediction, and if it's correct, then it'll be passive, so it won't change. But if it does get incorrect, it'll be aggressive, and then the model will adjust itself. So then for the next model, we have the random forest, which is basically a bunch of decision trees, and each decision tree makes a result for each sample. And then based on the end, each sample will have basically the majority of what all the trees said, and that'll be the decision that the random forest would make. And then so for our final one is the multi-level perceptron classifier, which is a feed-forward neural network. So how that works, we have obviously the input layers, the hidden layers, and the output layer. And then obviously what the goal with these models is to have different algorithms that will all help detect hate speech and tweets.
So for the very important part of our project, which is the attack on the model, what is an adversarial attack? So as you guys are looking at these two images, you're probably able to identify both as stop signs. But a machine or a predictive model that looks at images and determines whether it's a stop sign or not had no problem identifying the first image as a stop sign, but just by adding 3 lines to the second image, the machine was only able to identify the second image as a stop sign less than 1% of the time. So because this machine and these predictive models, they use an algorithm to predict certain things, there's a way to exploit that algorithm and find a weakness in it. So this is an example of finding a weakness in an algorithm, which is an adversarial attack. So why is this important? So say you're in a Tesla and you let it drive itself, right? So if the Tesla can't predict whether a stop sign is a stop sign, that is very dangerous. You could potentially kill yourself, you can kill a person, and there's a lot of danger involved. Yeah. So our attack system. So an adversarial attack uses adversarial learning, which essentially we as humans, we don't really know what exactly goes into a model, what makes it take something as input such as a tweet, and what makes it predict it as hate speech or not hate speech. So that's where adversarial learning comes in. And adversarial attack, it will take an input such as a tweet, and it will change it in a way to fool a predictive model. So there are 2 types of attacks. There's the white box attack and the black box attack. The white box attack, it knows about the model, and it will specifically use that knowledge about the model to exploit and find a weakness in it, and for it to output a false label for the data. We use the black box attack method, which is a heuristic method, meaning it will try out a bunch of things and until it's used that something works, so it doesn't have any prior knowledge of the model. So the two black box attack methods we use is the EDA, using data augmentation, and word embedding using Glove.
So for the first one, we have easy data augmenting. This one works in 3 primary ways. The first one is going to be through the random swap, which you can see is the big example up there. It just randomly swaps words with other words. The other thing it does is random insertion and random deletion of words. It's really simple but really effective at tricking models that have been trained on human speech.
Word embedding turns words into numbers so that computers can understand them better. Glove is a type of word embedding and is a pre-trained model that we use, which gives each word a vector of numbers which represents how often that word is used in context with other words. So for example, the word cat and kitten are used in the same context very frequently, so an input sentence such as the cat sat with the man could be changed to something like the kitten sat with the woman. This was the second text attack method we used.
So our results. So for the defense system, we had pretty good results. On average, on our 3 models, we had an average of 92% of classifying hate speech and non-hate speech. The lowest one being the random forest at around 91%, and the best one was the passive-aggressive classifier, about 93.5%. And generally, for all 3 models, they were better at classifying non-hate speech rather than hate speech.
So we also found the results of our attacks pretty effective. So after we took the tweets as input and we augmented them with the different attack methods, we found that the model accuracies went down by about 20%.
We also found that after augmentation, the word frequency was maintained. This is with stop words removed. So this is really important because it shows that the meaning of the text was the same. The hate speech was still there and was still identifiable.
Hateful language is typically predictable, repetitive, and simplistic. So because of this, the attack team expected that the augmented data would have more diversity of words than the raw data. We were successful in this in that mostly the lexical richness either increased or stayed the same after the attacks.
So, in conclusion, was our defense method successful? We think so because we had greater than 90% accuracy in identifying hate or not hate speech. And then were our attacks successful? Yes, we would also say that as well. Because after augmenting the tweets, we found that they maintained about the same semantic meaning, which is important because once you pass hate, you want to deceive the model, but you still want to come across as hate. And we also found our attacks convincing as well because we were able to drop the accuracy of our defense models by 20%. Thank you.
It's nice work, and my question is more regarding the data set part. Can you briefly go through the data set collection once again? Maybe in more details.
So our data set contains both hate speech and non-hate speech, and it was classified based on, as previously mentioned, academically annotated, and so based on people who annotated, they were classified as hate speech or non-hate speech.
Yeah, so is it binary or is it have different scales, like 1 to 5?
Well, the original data set originally had offensive and hate speech and regular speech, and they were classified as a different number for each one, 0, 1, 2. And what we did is we kind of combined the offensive and hate speech into one category so we can make it binary in our models.
Yeah, cool. Actually, I think in real research, one suggestion or observation that people find is that even if we have an annotation guideline, the human agreement on the labels are kind of ambiguous or they have different, I mean, a human annotator agreement is very raw. I don't know about his speech domain, but definitely I think the label space should be distributional, but not binary.
Just a couple questions, real quick ones. Out of curiosity, you guys use Glove. Did you guys try any other embedding spaces or different types of encoding?
We originally tried Word2Vec, but we were running into trouble with the collaborative space we were using. We were running it all on Deep Note, and we were having trouble with running into memory issues.
And kind of in the similar light, did you guys use any other variations with the embeddings? Like, multilingual, or is it strictly English?
Strictly English.
Gotcha. And the last one, you guys reported an accuracy metric. I was just curious what the accuracy metric was.
The accuracy metric just shows how much of the hate speech is being classified correctly as hate speech. So.
Awesome. Thank you.
Next up, we have River Optometry. Give it up to them.
Okay, hello everyone. Today we're going to be presenting to you our project, River Optometry, Underwater Object Detection by Shruti Karthikeyan for Sanawar.
For Monali. And Aditya Kulkarni.
Shout out to our amazing team lead, Ariana San, and our faculty advisor, Dr. Jonas Sadesi. Okay, so moving on to the introduction. Our project's objective is to achieve high accuracy underwater object image classification. And in order to do so, we utilized a low-light analog camera, and we fitted it in an airtight, waterproof container, which is then further utilized to capture images of underwater debris, such as plastic wrappers, plastic bottles, metal cans, and such, which was then processed using ACM, or a convolutional neural network model that we trained to detect trash in marine-like environments. So, for the CNN that we utilized for this project, we used YOLO V7, a version of U-Only Lufthansa architecture that specifically is designed for object detection, and we thought this would be best suited for our project. Now, if you're wondering why YOLO V7, it's because YOLO V7 provides real-time object detection and low inference times, which would be better and beneficial for object detection that would be moving, for objects that are moving underwater.
Now let's take a look at the dataset we used. Through a Creative Commons licensed dataset on Overflow, we compiled over 13,000 images of marine trash, such as plastic bags, metal cans, and more. After we obtained the viable dataset, it was time to train our model. As many of you may know, training a machine learning model is a highly GPU-intensive task. We utilized a custom Linux machine with remote access to train 200 epochs on a batch size of 4. This was the maximum viable amount of iterations we could do in the project timeframe. and this allowed us to acquire the necessary weights and biases.
And after weeks of training and experimenting with the model, we came up with the following results. To evaluate these results, we used the precision metric, the recall metric, the intersection of union metric, and the mean average precision metric. The reason why we have the mean average precision matrix at 50% is because even when there is a low alignment of the intersection of union, we will still be able to get an accurate image. The intersection of union is the model predicted bounding box over the bounding box in the data set itself. So the higher that ratio, the more average or the more accurate our model will be. And to my left over here is the precision graph. Precision is the measurement. Okay. Precision is the calculation where you have the true positives over the true and false positive. A true positive is a proposal where the object is presented in an image, and if it is detected, that's a true positive. If it is not detected, that is a false positive. And on the x-axis of both of these graphs, you see the epoch count. And epoch is essentially an iteration where the model learns from the data set through the training examples. After experimenting a bit, trying out various different epoch counts, we decided on 200 because we also wanted to avoid overfitting while getting accurate measurements. Next slide. And then to my right over here, you have recall. Recall uses the same calculation as precision, where you have the true positives over the sum of the true and false positives. But the difference is that recall is more for object classification, seeing if a plastic wrapper is actually a plastic wrapper. And next to it, you have the mean average precision from 0.5 to 0.95. The reason why we have these bounds is because getting anything over 0.95 would have too perfect of an alignment, and that is unrealistic in a marine environment. And anything over 0.5 is considered a good fit. On to the next.
So in terms of challenges, when we were looking for a data set through the RoboFlow website, we aimed to find a specific data set of the underwater garbage that specifically pertained to everyday metal or plastic items, so we had to look for that. In terms of low lighting, while we were testing, we required an optimal light source because we covered our fish tank around with tape and the top with a black cover in order to reduce external reflection. That is why while testing, we had to use a flashlight in order to put in sufficient amount of light within the tank environment. And because at the time our GPU capabilities were very limited, we turned to a custom Linux model machine. Special thanks to Lawson Lay and his team for lending it to us in order to train our model remotely. And finally, while testing, we aim to emulate an oceanic environment while controlling variables such as water level and transparency levels in order to help the model train as accurately as it can. In conclusion, through our research, we hope that we have been able to accurately create a camera that can detect objects as accurately as possible underwater. In the future, we aim to expand our data set to include more types of garbage and even beyond garbage, and we also aim to train our model even more accurately so that the camera can detect objects better. We also hope that our camera will be used in real-world applications such as nautical expeditions or search rescues in order to reduce manpower for safety concerns. Furthermore, for further exploration, you can check out the RoboSub here at UTD, who have been a tremendous aid to our testing processes.
And here's a short demonstration of what we've achieved. So in this example here, we can see that the plastic bag is being detected at a very high accuracy level. I'm not sure if you guys can see it there, but it's at around 85 plus consistently. And even as the camera moves and shifts about, it continues to detect it at a very high accuracy. And here, the light's a little off, but we used a Twix wrapper. That's what you see in the corner. And that's being detected as a plastic wrapper in this case. And if you see in the very corner, even as the camera shifts and moves about, the Twix wrapper is still correctly identified as a plastic wrapper. And the little reflection in the corner is luckily not interfering that much. One of the most successful objects we had to detect was the metal can. And this was really challenging though, because of the reflections we faced, if you can see in that corner over there. And then another challenge we faced was when we flipped it, the box loss was pretty great when it came to 2 colors. And yeah. And then finally, we have a plastic wrapper on top of a water bottle, like regularly. And we can see even in here, there's some minimal amount of reflection coming into the tank, and that's doing a little bit of interference, but we're still getting a very high classification as a plastic wrapper. Thank you guys for watching. We'll now move on to the poster and answer any questions from the judges.
Awesome demo, guys. Really good presentation. Just 2 questions. I'm assuming the batch size of 4 was because computational limitations. Did you guys try any other things as a team to sort of mitigate that, or like model reductions or mixed precision training?
We actually initially had a batch, a epoch count of 50, and that it's on our poster. We kind of demonstrated that it didn't really classify everything correctly as we wanted it to, and so we had to train it even more to get to 200 epoch count.
And along with the training, what were you guys using for loss function for this?
Just YOLO V7.
The loss function for it?
The loss function for it? I'm not completely aware of the loss function that YOLO V7 uses.
Oh, sure. Thank you.
So on the poster you mentioned that it's your accuracies are not, or your precision and recall are not up to industry standard. What do you define as industry standard? So what was your considered baseline? I know you had limitations in GPU, so you could not train another baseline, but what is the industry baseline? If you have it.
Well, ideally, we would want the recall score to be 90% because if you saw like just for split seconds in the demonstration how we were getting flashes of different objects being detected, which indicated a low recall score. So ideally, we would want to have that instead of like 90, 95.
So I guess my question is, where do you come up with the figure of 90 to 95? What's the reasoning behind it?
The reasoning behind it, well, it was just during testing, we went from not being able to like get the right object at all to getting high percentages on the object because the environment we are training for, it's a marine environment, so you have stuff like food coloring in the tank, and then you have like various other stuff too. So we want as high as a score as we can get.
Okay, thank you. I guess what I was trying to say is maybe your models are doing pretty well. I think if you have a future chance, you should compare it with other detectors or other methods. Because sometimes in object detection, in the image computer vision world, right, the precision and recall scores that all have are pretty impressive for a significantly difficult task than what is usually compared in the literature. So yeah, I think awesome job on, and I would like to especially mention that this is like a true industry level research project. You have a working proof of concept, so that's awesome.
Thank you. All right, thank you for your time.
Alright, we're going to take a quick 5 to 10 minute break because we're doing back-to-back presentations and we'll get started in a bit. Please help yourself to some pizza. We have a lot more, talk with amongst each other. We'll get started soon. Thank you so much.
Finding Security Vulnerabilities team.
Hello. All right. Welcome to our presentation. Our research topic is finding security vulnerabilities in IoT devices. Our lead was our lovely Grisset Barrow, right there. Faculty lead was Dr. Wei Yang, and I'm Daniel Wen.
I'm Ben Kai.
I'm Najali Habush. I'm Subika Sila.
And I'm Sam Preston.
So I want to ask, how many of y'all here use some kind of wireless earbud, or maybe a fitness tracker like Fitbit, or even a Nintendo Switch Joy-Con at home? Show of hands? Oh, I see a lot of you here. So as you can see, Bluetooth connected devices is becoming increasingly popular, and Bluetooth themselves predict that by 2027, the annual shipment of Bluetooth devices will be 7.6 billion devices. And because a lot of these connected Bluetooth devices have sensitive or may have sensitive data and are often connected to your phone, we focus our research on a JavaScript-based smartwatch, open source, called the Bingo JS2.
Alright, so for our project's initial exploration, challenges, and solutions to those challenges, the first one was actually picking an IoT device, because when we started, we didn't have the watch picked out already. And so the main challenge was, with this was that a lot of the devices we were looking to purchase were owned by private companies with like closed source proprietary software. And so though it was unlikely, we didn't want to run into like legal issues, you know, or like get put behind bars, because that's bad. And so we decided to go with the open source Bangle JS2. So once we actually picked out the watch, we noticed that the software that the watch ran on was JavaScript. And so our professor recommended that we use dynamic taint analysis using the tools Longitude and Augur. Basically what this would do is it'll track the data flow through a JavaScript like piece of code to try to detect any vulnerabilities in the code. The problem with this was that the Bangle.js apps that you could download and run were extremely primitive. It was like clock apps, you know, stuff with no real input data. And so additionally, like the frameworks that Longitude and Augur ran on weren't compatible with the watch. And so with JavaScript out of the picture, the other angle we looked at was the actual Bluetooth connection that the watch makes with the host. And so the challenge with this was we ordered the watch and it was like getting shipped from Europe. There was delays. And so even though we didn't have the watch, we researched the actual Bluetooth protocol, different like previous vulnerabilities and CVEs that were listed, as well as different pen testing tools used for Bluetooth. And so we had all of that ready. And so when the watch finally came, what happened? Well, to put it shortly, the watch had no security whatsoever, and I'll let Sam explain that.
Yeah, so basically, most IoT devices, I'm sure you know, have like a two-way authentication. Like AirPods, for example, you have to press a button to like connect to them. But this one, you just connect to it and it just accepts it, whatever the connection is. And it's designed to be connected to the Web Bluetooth API, so any Chrome browser can connect to it, which means that it's very simple to build a website to hack Bangle watches. So here's a website to hack Bangle watches. All you have to do is click connect, and after a while, a watch should appear. Not that one though. I don't want that one. There we go. And I'll actually give one of these to one of the judges. One of you can grab one of these and just hold it in your hand. And here I can type in whatever JavaScript I want. And you should have felt it buzz in your hand. So the way this works is the watch will accept whatever Bluetooth UART data it receives. UART is basically just like a stream of data. And whenever it realizes that it's JavaScript, it'll just execute it. So what we realized is because the watch is able to also make Bluetooth connections, we can make a primitive worm that can spread between different watches. So the first watch I gave you should be buzzing every about 5 seconds, like right there. And eventually, once it's able to actually connect to the other watch, if it does, oh, time out, it'll spread to the other watch, which will also start buzzing. Oh, disconnected. So while that keeps buzzing, we can go back to, let's see, fully ball buzzed. Yep, so it spread successfully to the other watch. So you can see why that's a big problem if you have a Bengal watch, is that you can easily connect to it. Now there is a limit to the range. Inside it could be around 14 to 15 meters, outside more like 8. We tested this by sending a 1 kilobyte stream of data there and back and recorded how long until it didn't work. But you have to be around it for like less than 2 seconds. So it's a very large window realistically, if being able to hack into someone's watch.
So the worm itself is pretty harmless when the watch has just the default apps loaded in. However, users have access to hundreds of different apps available on the website that they can download onto the watch itself. For instance, they can get 2-factor authentication. If a user wants to log into their Microsoft or their Google or Amazon account, they can use 2-factor authentication to send it to the watch. With the worm, we can intercept that cryptographic key and generate the 2-factor authentication code. On top of this, the watch uses something called Gadget Bridge. This is an app that allows the connection between your Bluetooth device and your Android device. This is specifically, there's a version of it specifically built for the Bangle that allows for HTTP requests through your phone. So on top of this, you have access to the user's notifications, their text messages, and even their location, which is incredibly dangerous in the wrong hands. On top of this, the Bangle also comes with a heart monitor. So users can use this in conjunction with any health app to track their health and their heart rate. And if a user relies on the heart monitor to alert them if they have high heart rate, any hacker that intercepts this and somehow messes with this could cause potentially life-threatening damage to an individual.
Throughout this process, we employed methods such as code analysis, penetration testing, and reverse engineering to find the different security vulnerabilities in IoT devices, such as the Bangle.js smartwatch. Our team created software that allows users to simultaneously launch a program to multiple devices. We found that even though Bluetooth low energy technology is efficient and easy to use, it has some inherent vulnerabilities that makes it easy for malicious individuals to access it.
So as the people from Bluetooth themselves put it, the relation between Bluetooth and security is that Bluetooth will offer you a kind of security toolbox to use. And it is up to the designer to use the tools in this toolbox to specify a certain security level that is fit for their product's purpose. Here are references, and thank you.
Any questions?
You have a good motivation for the project, but I wonder what is the current technologies being used for this tackling these vulnerabilities in industry or in the security research field? What are the related work and current standards?
The current standard, so as of right now, Bluetooth is, I'm not sure about the specific number, but it's at 5 point something plus. So Bluetooth Low Energy comes with Bluetooth 4.0 and Bluetooth 5.0 built on top of that to make it compatible with Bluetooth Low Energy and Bluetooth Classic. And so the standard used is the Bluetooth 5.0 plus specifications. That's for the Bluetooth protocol themselves, the security toolkit. Some of the tools that are used, they're being, I guess, developed. More and more tools are being used as like hackers are developing more tools. Some of the tools that are currently in use right now are things like BluePie or certain other Linux libraries.
So awesome presentation, and it's awesome to have a live demo. My question is, were these known vulnerabilities in the Bangle watch? Or, so if they were not known, did you all attempt to create a CVE and submit it as something you have detected?
We didn't look into making the CVE. We're not quite sure, first of all, how to do it because I never looked into it, but also specifically what the vulnerability would be, because it seems as like a major like design oversight. There are like actually the watch by default has like a whitelist for like only accepting known devices. It just doesn't work. And also there's a passkey feature that's in beta that's supposed to require a PIN for you to connect to it. However, that also doesn't work. So looking into those would definitely be a great specifics for CVD. So
yeah, that would be a good idea. You could always also report it to wherever. I mean, the customers would usually buy more, like on Reddit or any open source, on any social media as well, to just raise awareness of the issue, because this is something important for customers to know about. So yeah, that there's some impact.
thank you.
Next up is Agent Chase.
All right, ACM, what time is it? 10:15, how are you guys doing? Right, late night. All right, so we are Agent Chase. My name is Michael.
I'm Ahmed.
I'm Vivi. And I'm Navina.
So this is Agent Chase. It's pretty much a two-player game, similar to Capture the Flag. And there are two players, also known as agents. You have the attacker and the defender. So the objective of the attacker is to reach the goal while also avoiding the defender. And the objective of the defender is to get the attacker before it touches the goal. So we trained two AI agents to learn to play the game, and we did this by making the agents play against each other. So at the beginning, there was very random movement when we started training, but as the AIs were training, they started to learn through trial and error what to do and what not to do. And now to move on to the game design, we'll be passing it to Vivi.
Alright, like Ahmed mentioned, here are the two agents among the scene-inspired agents that we made. And to train our two agents, we use something called proximal policy optimization, or PPO, which is a reinforcement learning algorithm that really helped us create all these complex environments and train in it. And what we did was we gave our algorithm the position values of our three objects, with the three objects being our goalie, the defender, attacker, and the goal.
And at its core, what PPO does is it really incentivizes the agents to either do an action or not do an action based on the reward system that we made. So let's assume the attacker is going towards the goal. We would give it a positive reward because, well, it is a part of our objective, so we like that and we would want to do that. And I can also put it into perspective here. So let's assume Ahmed is training Michael to do a certain task. And let's say Michael successfully does the task, then Ahmed would give Michael a reward. Let's assume Michael does not do the task very well, then well, Ahmed would slap Michael. And we would apply the same logic to our agent scenario. So the attacker really wants to go to the goal and would get the most points for doing so, and the defender would want to tag the attacker and would get the highest reward for doing so. And we also had a few other rewards, or rather penalties in place, like the time penalty, to make sure that the defender wouldn't just like stall or sort of just camp near the goal, but hopefully this gives you a gist of what we did. And now that you hopefully understand the agents, we can go into the environmental design. Right, so we used Unity, which is the 3D game engine, to implement our environmental design, and we really used Unity for two main packages, the first one being ML Agents, which really made coding AI a lot easier on our end, and we also used the ProBuilder package, which made making the map a lot easier on our end as well. And that picture right there is our first prototype that we made using ProBuilder. You can see the goal in green, the attacker in blue, and the defender in red. And the positions of these three were randomized for each session that we did. However, the walls were always stay stagnant, and the walls really made sure to sort of provide a challenge of sorts to our two agents. And later on, this is our final room, or map, and what we did was we imported a post-apocalyptic CSGO-ish map, just for the aesthetics. It's important to keep in mind that this doesn't really do anything to the behaviors of our two agents. It was just there mostly for aesthetic purposes. And now that you hopefully understand how the agent and the environment work, we can go into training.
So we start off with early training, and as you can see in a little bit, the agents are kind of dumb. They keep running into walls, and they don't really have an idea of where their rewards and what they should really be doing in the game. But as we move on to mid-training in a little bit, we see that the agents have a little bit more of an understanding of what to do. So right here, we see that the agents have more of an understanding of what to do. They're no longer ramming into walls as often, and the attacker knows to get the goal, and the defender knows to circle around the attacker to prevent them from getting the goal. And as we reach late training, we see that the agents are no longer running into walls, and they're doing much better. We can see that the defender is constantly circling the attacker, and the attacker is trying to get to the goal, which happens sometimes, but not really. And that concludes training, and on to Michael to discuss some of our results.
Alright, so I have two graphs for you guys. The first one is our cumulative rewards over time. The purple line represents the progress of our defender. The orange line is representing the progress of our attacker. As we can clearly see, there's a bit of a mismatch going on here. Our defender, he gains some steady rewards over time, clearly getting better and improving. Our attacker, on the other hand, remains stagnant. Now, we gotta remember that these graphs are to scale to fit. So, as shown in the video, our attacker is indeed improving over time. However, it's like trying to compare yourself to Usain Bolt. If you are running, let's say, a race against a 5-year-old, and you go and you lose like 0.5 seconds. Not a big deal, right? But if you lose to Usain Bolt by 0.5 seconds, you're really good, but it's still Usain Bolt. He's going to beat you. Now, this is shown once more in our value loss graph. Value loss representing our agent's ability to predict the outcome of their next move. Once more, we see that our defender is leaving our attacker, well, in the dust. Now, there could be two possibilities for why this happened. One being that our attacker needs probably a modified reward system, maybe a little more motivation to reach that goal and get past our defender. Another possibility, well, implies one of the bigger issues when it comes to asymmetrical multi-agent training. And that is that one agent can very quickly begin to outperform the other and stunting the other's growth in the process. Moving on, I will pass this to tell you guys the challenges that we had while performing this project.
So one major design challenge that we faced was having some of our random objects spawn into other objects. So as you can see in the first picture.
Yeah, so during the training process, we encountered a setback with the ML Agents installation package guide. So that guide that we used to install ML Agents, it was just outdated and it wouldn't work sometimes. And the Python packages themselves just weren't compatible. So what we did to fix that was we created a virtual Python environment and we one by one downgraded the versions of each package to make sure all the packages were compatible with each other.
Our agents also lacked raycast vision at the very beginning, so their training was very slow. So once we added that, the agents were able to train a lot faster.
And like Navita said, our training was very slow initially, so something else we did to make our training faster was we duplicated our initial environment, and we ended up with 16 environments, like you can see on that picture. And that really quick helped us sort of make our training process faster, and it helped us come to a few conclusions.
Through the completion of the project, we concluded that PPO is viable for multi-agent training, even when the agents themselves have different goals. And ML Agents provides the foundation in Unity for reinforcement learning, rather than us having to create a new system from scratch. And in other multi-agent systems with different goals, one agent may overpower the other. And yeah, thank you.
We would like to thank our faculty sponsor, Dr. Rodzi, as well as our team leader, Naveen. We love you. So, yeah, thank you for that.
I have to know, how long did that slide take?
Which one?
To make the whole slide deck.
The whole slide deck? 2 days.
Too long. It was really awesome.
Thank you.
What was up with the cow?
The cow? That's a bit of an ACM research inside joke. If you know, you know.
Gotcha. Serious question now. What type of, you guys said you created the reward system. How did you go about that process? Would you initially have as a reward system to change it all for rewards and penalties?
Okay, so our reward system, the concept of our reward system was probably one of the very first things we dived into when we thought of this project. We brainstormed many possible ways. We ended up with a couple different, however, both agents have essentially the same values, but a different goal. So these values refer to them getting closer or farther away from the goal. So if an agent gets closer to their goal, they're rewarded. If they're getting farther away from their goal, well, they're penalized. If they hit a wall, they're penalized. If they reach the goal, of course, that's their win, right? So that's their highest reward. Versus if their opponent reaches their goal, well, that's their loss.
It's an awesome presentation, and from my understanding, there are also like language games with reinforcement learning. And I think for OpenAI, they also developed I think PPO was developed by OpenAI. It was motivated by their product need or research need. Developed the reinforcement learning algorithm for gaming and in the 3D environment. And I wonder what is the motivation for you to work on this specific task of doing agent chasing? Why don't you try like other tasks or games?
Well, there were a vast ocean of possibilities for picking this project, and we won't lie, YouTube channels, there are a lot of YouTube channels out there that play with the ML agents, and they were a big inspiration for us. However, most of them were training a single agent, and that is why we wanted to try and see what would happen if we had two opposing agents go against each other.
Also, to add on, we initially had a lot more things we wanted to do. So we had sort of like a system where we would have all these power-ups laying around the map, and we would have the agent sort of choose between what to do, between doing the power-up or sort of going around and chasing and all of that stuff. Initially, our map was actually a part of an Among Us map as well, but because of the time constraint, we ended up having to sort of just make it like a little square, and we made it a little like what it is right now. Thank you.
Cycle game, color image translation.
Some technical issues here, obviously, give us a bit. There we are. Hello, ACM. I know it's pretty late, but we are the Clean Image Translation with CycleGAN team. My name is Ryan Joseph.
Mine is Omprene Blurry. I'm Mortazo.
I'm Tommy Bala.
I'm Nidek Koya.
And we have our wonderful team lead over here, Ben. And we also have our faculty advisor here, Dr. Yang Tian. We want to thank him first of all. And let's get started.
All right, y'all. I want to start this presentation off tonight with a question. Can you guys raise your hand if you've used ChatGPT before? Get them high. I know all of y'all have. All right, of course. What about Dolly? Y'all used that before. It's pretty cool. And have you guys seen this TikTok filter up here? Yeah? I mean, I'm sure y'all are TikTok addicts like I am. So, I guess what we can start out with is, we've seen tremendous improvements in AI over the past couple of years, right? Like, ChatGPT literally answers questions for you guys. Dolly literally, translates text into images for you. And this TikTok filter right here translates a real-life image into an anime image. But how does this work? Well, an image translation network is fed thousands of images to make this work. An example of an image translation network is CycleGAN. But what exactly is CycleGAN?
So first and foremost, GAN stands for General Adversarial Network, and that's where we have two neural networks that work off each other using a variety of deep learning methods to produce accurate predictions. Or in other words, where we have a program that essentially trains itself over and over again to produce an accurate result. So CycleGAN is a technique where we automatically train image-to-image translation models, and we essentially use these two neural networks, which is called the generator and the discriminator, to produce an output image that's similar to the given input image. So the main function of this network is that it's taken in a data set of input images and output images, and it uses that to create a lot of applications. For example, this image here, where we have a horse as an input image and it gets converted into a zebra, and vice versa. So we use this technique to create a model which takes in pretty much discolored and cloudy underwater images and convert them into clear and appropriately colored versions of themselves.
So the first step into creating our model was data collection. Our model specifically needed two different types of data, paired data and unpaired data. We obtained our unpaired data from the University of Montana's Interactive Robotics and Vision Laboratory, and it contained over 7,000 images of underwater objects and creatures. Now, coming to our paired data, let me explain what paired images are. First of all, as you can see here, we have a car, which is an object, in cloudy water, and another picture of it in clear water. So the image on the left is the input image that you would be feeding to the model, and the image on the right is the expected output. So we decided to take the images ourselves. So first we obtained an underwater camera, and then we had a transparent container box setup in which we placed around 141 different objects and took images of the objects first under clear water and then under cloudy water. And the important aspect of this process was to ensure that the angles and positioning of the objects were the same in both cases. Right after this, we went directly into our model. Our model is a semi-supervised model in which, as you saw in the previous slide, uses both paired and unpaired data. So why did we pick this model? First of all, it is a newer and more efficient model, and say our model is an underwater data set, and there are a lot more unpaired images available than paired images. So for our model, first, we did it in two steps. The first step was to use the paired images to make a basic supervised model that could detect image patterns and colors and make the model quicker to detect newer images. And then we introduced our 7,000 unpaired images to the model to make it more accurate.
So our CycleGAN network basically had two discriminator networks and two generator networks. So what the generator networks do is they produce fake images. And the discriminator network determines the difference between the real input image and the generated fake image. And basically this process keeps on going and going until it's very, very hard for the discriminator network to determine which one is real image and which one is a fake image. And to get a result, we basically used a total of 4 loss functions. So as you can see in our images, we had an original input image, real image A. We used generator from A to B to get a fake image B. And then we used generator from B to A to get a fake image A. So this is basically cycle loss. So cycle loss basically is essentially that the generated image from A to B is the same thing as a generated image from B to A. And then we have paired loss. So paired loss is only for our paired data, which is our supervised part of our model. And we use a discriminator loss to determine the difference between that real paired image and the fake generated image that we generated earlier. And then fourth loss function is identity loss. So what identity loss does is as our image goes through the generator network, it makes sure that the identity of the image isn't lost. And in the next slide, you can see our images that we got from our 4 loss functions. So on the left side, you can see this is our original input image. So it's underwater, it's all green, it's not very clear and not very color accurate. But on the right side, you can see the object more in detail. It's more color accurate and it's more represents real life.
So of course, with our development, we faced some issues. First one was figure out what our data set would be in that case. We were debating between X-rays and security cameras until we finalized on underwater imaging. Seems nice. Another issue we ran into is with our tensors. We had to convert our images into tensors, and how we properly separate our paired images from our unpaired images. We figured out by adding a few messing with our dimensions, and we got to a reasonable way to determine between the two. Finally, an issue was with our output. We had to figure out how to get a more accurate, more good output. That was messing with our loss functions and calculating until we got a more reasonable, more human, more human readable output. Now, some applications of this model. Obviously, it would be underwater photography, both in scientific and general. I know it's almost summer, right? It's almost beach time. You're going to go to the ocean, go snorkeling. You want some good photos, right? This model can help clear up those good photos. Maybe you want like a dusty area, maybe it's a sandy beach. Hey, this model can help with clear those photos and make those pristine, beautiful photos. In scientific models, scientific applications, hey, it can be better for research, better for general analysis of underwater environments. Robotics. I see you, we're a rover right over there. Are y'all over there? Hey, maybe it's going to be a beautiful relationship here. We could use some of our accuracy, maybe some of our, maybe we can make our images look nicer to help y'all out with your, color image, with your computer vision. This could be the start of a beautiful relationship, man. Listen to us, call us, it's a call. And finally, security. That's not exactly, we have to modify our model a little bit, but easily we can use our model to be improving security camera footage, enhancing it to a certain extent, if it's like in rain or in difficult conditions. It can be very useful in those security camera footage. So, next. So, generally, our conclusion is this model allows us to clear up our images in a more usable manner so that it looks nicer and more color accurate to what would be reality. Adding more images, adding more different environments, as we saw with the rover. We saw with darker colors, darker image in deeper water patterns with less light. It will allow for better image conversion, it will allow to better image translation. So just nicer photos with whatever input you put in there, you should get a great output at the end. In that case, thank you for the presentation, and any questions?
Yeah, nice presentation. So my major question is about the evaluation. So you presented some results of the picture underwater and the picture, the generative image. So did you do other tests, or how did you compare the performance or the effect, influence of each loss term with them all? Or do you only do like one training and one testing?
It was a lot of human interaction. We had a lot of issues with our loss functions with hyperpigmentation and our images coming up extremely highlighted, which is to the point of unrealistic. So it was a lot of trial and error, a lot of messing with our loss functions to get something that's more reasonable. That's not looks like it's radiation, to be honest. So yeah, something that actually looks nice. Do I answer anything? Okay, sure.
So when we first we started with the unsupervised part of our model, which basically gave us an okay output. And then we had to add the semi-supervised part of it, so we had to add the paired loss function. So we created our own paired loss function. So after we did that, we had a lot more errors because that's what caused the hyperpigmentation and stuff like that. So that's what probably, we had to do a lot of trial and error until we got a good looking output, and that's what we determined. That looks like a good looking image that we would want when we input underwater image. So that's how we determined that the model actually works.
I see you guys highlighted a lot into qualitative results. I was just curious if you explored any metrics or comparisons for quantitative analysis.
Not really. Again, it was mostly a human analysis onto the quality of the photos. Definitely, we can make a quantitative analysis to give more detail to it. But right now, our model is based on a more human approach to it.
I think the only quantitative part of it was we printed out each loss. So we basically found how much loss each part of the loss functions did. Since we had 4 different ones, we found how much loss each one did and compared that and made sure it was actually working.
Thank you.
Thank you.
All right, next we have our second to last team of the night. Give it up for Nerf or Nothing.
This works. Okay. Yes, it's on a different computer. We're just going to plug it in, do a real time rendering. All right, we got this. Yeah. Yeah.
Rocking.
Just wait till you're ready, okay? Now change slides.
Sure. And you're watching the script, right?
I'll be able to set up the. Maybe I won't be able to set it.
All right, as the third graders ahead of us have also talked about, it's getting pretty late, so we're going to go ahead and get right into it. I'm Rowan White, I'm a CS freshman.
Hello, I'm Ann Nguyen, I'm a CS freshman also.
Hello, I'm Yusuf Wadi. I'm a CS junior.
Hamza Dwayne, CS senior. Yes.
And tonight we're going to be presenting our team's research project, Nerf for Nothing, Measuring Immersion in Neural Radiance Fields. As y'all can see here, this is a Nerf gun. And unlike what our name might suggest, it has nothing to do with our project. This is actually what we're talking about, neural radiance fields Nerfs. This is a novel new approach to view synthesis, which is an issue of generating new views of an image based on, or of an object based on just a few images. For example, I want to be able to take maybe 4 pictures of a chair, front, back, left, right, and from that be able to work backwards and generate what that chair looks like from all of the angles in between. All right, for the nerds out there, the way Nerf does this is by representing a scene as a continuous function and then training that with a multi-layer perceptron, or MLP. It takes a 5D input coordinate, the location X, Y, and Z, and the viewing direction theta and phi, and it outputs the volume density and the view-dependent emitted radiance at that location. It can then generate new views by querying that MLP on array, starting at a camera location, going through the scene, and generating those densities and colors at a specific pixel. It will then get that color from the radiances and the densities using traditional volumetric rendering techniques, and then do that for all of the pixels in the image. So why does this matter? Why Nerf? Well, Nerf opens up the opportunity for faster rendering of more immersive, realistic scenes and objects. It takes into account information that older view synthesis methods such as photogrammetry don't, such as reflection and light. So in reality, what it's doing is it's giving us a new way to capture our reality. It's have applications in game development, visual effects, and even in, as you can see here, online home tours. But it's not without its limitations. So what we're doing is we're measuring the current capabilities of Nerf as it relates to immersive environments. We're looking at different Nerf models and different ways of capturing and processing the data that it uses. So to go into our methods, here's Ham.
Thank you, Rowan. Okay, so quickly, to test out the immersion factor of Nerf, we set out to capture unique scenes from all around the UTD campus, and in doing so, we were looking to answer 2 main questions. The first being, does the method by which we capture the data affect the quality of the Nerfs that are produced? And we also wanted to know, how do these methods respond to these different scenes? And so to answer these questions, we came up with 3 distinct ways to capture the data. The first being using an iPhone 12 Pro to capture standard footage. And then we also had a professional camera, the Insta1RS, which was capable of capturing 4K footage. And with the Insta1RS, we actually had a 360-degree attachment that allowed us to capture 360-degree footage as well. And so with all that information, we were curious to know, what is the current standard for Nerf technology able to produce with all this information? And so, as you might be able to tell here, we actually have 18 different videos. That's 6 distinct locations, each of which is captured with the 3 aforementioned methods. And so when we were capturing this data, we went out of our way to ensure that there was just enough variation to be able to expose any potential limitations within Nerf technology. And so we'll have some dark scenes, we'll have some lit scenes, reflective scenes, normal scenes, and of course some outdoor scenes as well. So with all this information, it was now upon us to try to reformat the data in a way that the Nerf technology will be able to understand and train upon. And so essentially what this meant is that we had to calculate the position and angle for each significant frame within the video so that the Nerf would be able to tell where it is in space. And so what we did in order to do this is actually we used a general purpose 3D reconstruction pipeline software called Colmap. And what it did was it took in our videos as a collection of images, and it uses a collection of images to reproduce the 5-dimensional coordinates so that we can use that. And so this is actually what we did for the 4K videos and for the 360 videos as well. But for the iPhone, we actually ended up using an application on the iPhone itself, which is a 3D LiDAR scanner that calculates in real time the 5-dimensional vector, so that was readily available to us. And so with the data sets created and the frames labeled with their 5-dimensional coordinates, I'm going to go ahead and pass it off to Yusuf so that he can explain the different types of NERF technology that we explored.
All right, let's get right into it. First, we have vanilla NERF, or the original NERF implemented in 2020. This model is the foundational model from which all subsequent models are derived. It is in essence a neural network that spits out a color given a specific viewing angle and position. The vanilla NERF spits out a realistic rendering or a realistic radiance, but it's burdened by a massive neural network that is heavy on training and querying. Next, we have Google's MIP-NERF. MIP-NERF improves upon the original NERF by borrowing from computer graphics, something called MIP mapping, it's called MIP mapping. What this does is, rather than sampling simple point rays, it samples a cone or conical frustum. What this allows is a smoothing out of the edges inside of the rendering. So this allows reduced aliasing, reduced blurring, increased computational efficiency, as well as higher fidelity in the fine-grained detailing. Think about it as the difference between drawing with jagged 90-degree angles and drawing with smooth outlines. Next, we have Nerfactor, which is almost like a kaleidoscope of NERF technologies and methods from the community API over at NERF Studio. Nerfactor uses a suite of different techniques, including, but not limited to, camera pose refinement, per image, this one's a long one, per image custom accumulation, and then scene contraction. And then next we have NVIDIA's Instant NGP, which is my favorite one. Instant NGP, or Instant Neural Graphic Primitives, is a method from NVIDIA that uses multi-resolution hash encoding. What this means is that they basically just threw a hash map at it. But seriously, they use a multivariate scale of hash tables in order to boost lookup times, as well as allowing for sparse encoding, also known as dictionary learning, and also efficient computation. By using hash tables, this also allotted Instant NGP to use the most beneficial factor, which is much, much smaller neural networks. By using these smaller neural networks, we achieve orders of magnitude in speed in training and rendering as compared to traditional NERF methods. And yeah, that's a bit about it for the models. Let's move on to our implementation.
All right, for implementation, we use the API NERF Studio, which previously mentioned have their own native method called Nerfacto. And the API is really convenient to use because everything is handled in a pipeline, training, rendering, viewing, etc. And it has all of our methods that we want to train with. And for evaluation, we judge the training model for each of the camera capture method, 4K, 360, iPhone / Polycam. And each of the type of data set, standard scene, light, dark, outdoor, indoor, and a few other variations. And the factor what we judge them on is GPU usage, memory usage, quality that we notice, and accuracy compared to ground truth. And then for processing, we use GoMap as previously mentioned, and with the 3 different type of capture method, 4K take about 2 hours to process, and 360 data take about around 9 hours because NERF Studio is tailored toward forward-facing scenes, which is like the standard forward-facing scenes. And then with the iPhone datasets, we use a third-party app, Polycam, to do that, which take around 10 minutes, which is quite an improvement from the 9 hour and the 2 hour. And moving on to the training. With vanilla NERF and MIP NERF, for each model, it takes around a day and a half to train per model. And when we use those two methods on the standard data set given from each of the NERF methods and our own our own custom data sets, when we use it with the provided data set, everything runs fine as expected. When we use it with our own custom data set, there's quite a few error, especially when in an outdoor scene, when the trees in the background of a scene is quite inaccurate because it's not in the focus of the scene. And then moving on to our other two methods, Nerfacto Instant NGP, their upsides is that they're quite fast with Instant NGP around 30 seconds, which is very, very fast, and then with Nerfacto around 10 minutes. And then their downside is also not being very good in quality because of the limitation of the Nerfacto pipeline and the overall time constraint on just training the model and having repeated runs of the data sets and overall. And to wrap up on all of the methods, they all have flaws of if you were to generate a new native scene that deviate a lot from the given camera scenes, then there would be quite a lot of error, and even then nothing could show up. And I will hand it over to Yusuf.
All right, real quick to wrap up, we concluded that it's not ready for most immersive or commercial applications. This is due to the fact that, as we saw with Vanilla and LibNerf, they took nearly a day, or even up to 42 hours to train a single scene. And then we also saw that with Nerfacto, 9-10 minutes, Instant NGP, 30 seconds, which is good, it's getting there. But there is a real potential, however, it's not currently there. I would want to mention with VR, it is really getting there.
All right. Do we want to try and do a demo? I know we're running short on time, but we can pull up Instant NGP and render something in about 20 to 30 seconds live if you don't like to see. No? Okay. I'm saying no. So we ran into quite a few roadblocks with this problem. We ran into scope creep, resource limitation. That 3090 was not cheap, and we were also doing the other projects and all of our methods with a bunch of different data sets. So resource limitations and time constraints were a really big thing. So we looked at the final products, but we also looked at the limitations surrounding them, given our resources and given the complexity of the thing. So thank you to ACM and the directors for the funding and the space to research this fascinating topic. Thank you to our faculty advisor, Dr. Xiao Hugo, for advising and guiding us. And thank you to Lawson for the funding and leadership. Without you, it would not have been possible. So thank you, everybody, for watching.
No questions.
No
Good.
questions? Okay.
Saves us some time.
All right, now it's time for our last and final presentation. Give it up for Bespoke Traction Protection Team.
Imagine this, little Timmy's having the time of his life, swinging and singing Shakira on top of his lungs. And bam, he falls down his arm. And before you know it, he has a fractured arm. His mom rushes him down to the ER to get his arm diagnosed. The doctor has the x-rays upside down, scratching his head, trying to figure out what's wrong with little Timmy. And before you know it, the doctor goes, "You're fine, little Timmy, just eat ice cream and the pain will go away." Mother Timmy knew that this was the case, so they rushed down to another hospital, and little Timmy is diagnosed with an AI model. And little Timmy is so astonished that he makes a TikTok and it goes viral. So sit back, relax, and let's explore corpus fracture detection using YOLO V7 as a tool for doctors. And hi, my name is Alima Kari.
I'm Larissa Tassin.
I'm Yukel.
I'm Amal, and these are our faculty advisors, Chris, and then Anjum Chia is our faculty lead.
And this is a quick overview of what you guys will see in the presentation to come. And with all this being said, currently there is shortages of radiologists, and a lot of radiologists are understaffed or undertrained. Hence, they make a lot of misdiagnosis. So with this, we trained YOLO V7, an AI-based model, to help diagnose these risk factors and injuries in patients. So with all of this, there is an upward of 3 to 5% of people that are incorrectly misdiagnosed, and about 25% of patients that are misdiagnosed in ER settings at night. Hence, with all of this, within 5 years, they form instabilities and deformities in their bones. And this is our data set. It consists of 10,000 wrist radiographs from the University Hospital of Graz in Austria, with patients ranging from the age of 0 to 19. And there's a total of 9 classifications, which can be seen from the bottom right picture. And this data set consists of annotations and images. And now on to Vimal to discuss the model.
So the object detection model in question is YOLO, if you haven't heard of that one already from the previous ones, but it stands for you only look once, meaning that it only requires one pass into an image for it to generate the bounding boxes and probabilities for the object detected in that image. Using a deep convolutional neural network, as seen in the image on the right, it gives a high-level pipeline of that CNN, basically extracting the features into a convolutional layer, and then pretty much putting that feature pyramid network into separate YOLO loss functions, and essentially just concatenating them at the end and just generating the bounding box probabilities. We use YOLO V7, as you see on the graph on the left. It's much faster and more accurate than the previous iterations and versions of the YOLO algorithm, but we also wanted to use YOLO V8, which is the latest algorithm in YOLO that was only released very recently, only a few months prior to the start of this project, and we wanted to just compare YOLO V7 and YOLO V8 and try out what those results will lead to us when training our X-ray and wrist data set. So now we can move on to the results. So starting with the pre-trained model, we found this pre-trained model that was trained on an X-ray radiograph dataset online, and we wanted to see how it would be evaluated on our own dataset. So we applied this on our validation part and achieved the metrics on the top row, and we wanted to see if we could improve upon that. So we trained our own YOLO V7 model using the pre-trained model's PyTorch file as a way to learn and improve upon that, and we got a significant improvement in precision over like 0.1, and then a slight decrease in recall with an overall increase in mean average precision with the IOU intersectional reunion threshold at 0.5. That seemed the most stable and the most industry standard IOU threshold to be. And we wanted to do the same thing with the YOLO V8 model. So once again, we trained it using the pre-trained model's PyTorch as a weight, and on the Google Colab Pro environment and GPU standard, we got an improvement in precision once again, with another slight decrease in recall and a negligible difference in mean average precision, similar to that of YOLO V7. And I have the formulas of precision and recall and mean average precision, but essentially precision in this context tells us that of all detections, X% of them were fractures, which we're looking for, and recall tells us that of all fractures, X% of them were detected. And mean average precision is simply a way and a more common metric in object detection of evaluating the overall performance of the YOLO model. And now we can move on to Yokyung, or actually demonstration of these results first. So the set of images on the left are images from our data set of the wrist bone radiographs. The labels are medically annotated and labeled by the University of Graz team. And the set of images on the right are those same exact images, but fed into our YOLO algorithm and spitting out their own label box, bounding boxes, and probabilities of where their fractures are, as located by those tiny small red rectangles of the fracture locations. And basically, for the most part, we see very accurate locations and diagnoses of where the fractures are, but we wanted to highlight the green circles where our YOLO model did not find a fracture where it should have found a fracture, as well as the red circles where the YOLO model found a fracture that actually wasn't there. But for the most part, it seemed pretty accurate. And now Yokyung is going to essentially visualize these metrics.
So now I'm going to be discussing about the confusion metrics. So basically, it shows the percentage of each labels that were correctly detected by our model. And we can see the fracture has 0.9 accuracy, which is quite high, and which was our ultimate goal of this project. And we also can see that we got a high accuracy for metal and text. So briefly explaining about the metal and text, metal is some metallic structure, artificial structure that we can insert in the bone. And text can mean the R or L text block that we put next to our arm when we take the X-ray. Yeah, next slide. And going into deeper, this is the precision recall curve. So if you remember the formula for precision and recall in the previous slide, high precision basically means low false positive rate, and high recall means basically low false negative rate. So it's better to have larger area under the curve to see to prove that our model's performance is good. As I mentioned before, we got a high, larger area under the curve for fractures, text, and metal. So the last method of evaluation is F1 score. F1 score actually ranges from 0 to 1, and it takes into account both precision and recall, and by taking the harmonic mean of them into the formula. So if the F1 score is closer to 1, it means the model's performance is better. When we look into the x-axis, there is a confidence. So confidence basically means the probability of the model's detection is correct. So it's better to take high confidence if the F1 score is similar. When we look into the red curve, which is fracture, we can see that it has the highest F1 score around 0.9 at the confidence value of around 0.5. So it's desirable to take a confidence value of 0.5 for further evaluation calculation. And from now on, Vimal will discuss strengths and limitations of our model.
So starting with the strengths, as you saw in the previous slides, it was validated on 8 other features apart from the fractures, such as like bone lesions, bone anomalies, and metallic structures that could be further trained upon and explored to be used in medical diagnoses other than fractures and wrist bone detection. We also got a good age range in our data set that captured from 0 to 19 years, which should be applicable to most pediatric departments if they want to put that into practical use by using this machine learning model. Some limitations, the biggest one being our huge data set size. Over 20,000 images and labels led to a data set size of over 16 gigabytes, which is just hard to move around, hard to augment. Essentially had to compromise some of our environments when we were performing them, as well as tweaking down some of our hyperparameters, specifically the epochs, down to a number suboptimal than it should have been for a number for like a data set size this large. And we also had the same sort of a consequence for a model size when we're specifically talking about the YOLO V8 model, which came in different sizes, and we had to pick a smaller one due to the amount of computational complexity and training times that would be required for larger model sizes and training our entire data set. We also highlighted there might be slight possibility of biases detected in our machine learning model, as some of the images that have fractures on them could be seen as a very shallow outline of a cast on their wrist bone, which may act as a confounding and influential variable in like artificially boosting the image of having a probability of having a fracture. But other than that, we can move on to the applications.
So across the nation, there's been a huge shortage of orthopedic surgeons, mainly due to the amount of time and effort it takes to become one. So our model is aiming to aid or possibly even replace surgeons where there's a lack of them. Also, misdiagnoses due to human error is a substantial issue, especially in high-stress environments like in an ER or late at night. Misdiagnoses become a lot more common. So our model is aiming to confirm diagnoses made by humans to help increase the accuracy of diagnoses. In conclusion, we've created a model that can detect fractures with high accuracy, as you've seen in previous slides. And our model can help assist radiologists in speeding up the process of diagnosis. Additionally, with confirming diagnoses and increasing the accuracy of them, we can help improve patient outcomes and potentially reduce healthcare costs in the future. And these are references. Thank you so much for listening. Love to meet you.
concludes all of our presentations. Thank you guys so much for listening, and thank you for all the teams for presenting. So for the final awards, we actually have 2 awards this time, crap. We have 2 awards this time, so there'll be a Best Research Presentation Award, which will be the best presentation decided by our 3 judges, and then there'll be the People's Choice Award. This is the award where all of you guys get to vote on who your favorite presentation was, and the team with the most amount of votes gets the prize. So I'll give you all a couple seconds to scan the QR code and vote. Pranav, can you give him permission? Hold on a second. We're gonna work on that. Cue the Jeopardy music. Give him permission. You good? Apologies for this. In the meantime, judges, you 3 can decide on who you think the best presentation is. You guys can talk amongst yourself. Sorry? Try it now. It should work now. So sorry about this. We're working on it. In the meantime, I guess think about your choices. Or, yeah. So while we're waiting, oh crap. While we're waiting on the People's Choice Award thing, I would just like to take a second to announce the new officers of ACM Research. Yay! All right, we got 5 new leads. Number 1 is Rowan, Victoria, and Monty. We got Philip and Nevada. And then finally, our new ACM Research Director, Aria. This semester, I just want to say 2 things. This semester, I really was trying to like change research. I don't know if some of y'all came to last semester's thing, but it was definitely a lot different from this, you know, with different projects, a different standard. And the projects that y'all presented today were really, like, they were like up to an excellent standard. And I'm super proud of every single one of y'all for the amazing projects that y'all come up with. So no matter who wins or loses today, I think everyone is a winner. And I know that's cheesy, but I genuinely feel like that. So y'all should get a round of applause for yourselves, because all the projects are so good. Yeah. Cool. Okay. Back to Jeopardy music, I guess. Please scan the QR code. Can I get a yay, nay, is it working? Woohoo! Yay, okay. I'll give y'all a couple minutes to vote for your favorite presentation, and then we'll announce that.
Don't do that, otherwise
I mean, isn't that how popularity contests usually work?
signed the form before I made an announcement earlier, you got to do it again. So if that kind of thing happens, I don't know what to tell you, because like it kind of ruins our videos. Don't do that. Alright, that's all I gotta say. So let's scan again, scan again. Scan again.
What he said.
If you're curious if you think your response is true or not, it should tell you if you've already submitted or not. Yes. Okay.
Lots of discourse and animosity in the Google form, we have come to a conclusion for the winner of the People's Choice Award. Give it up for, can I get a drum roll? The winner is Finding Security Vulnerabilities in IoT Devices team. Wait, I need to get that. Y'all can come up to the stage.
Wait, Alessio, you should come here. I need to do like a crowning moment. Congratulations. Yeah, congratulations, graduated. Congrats. Oh, sorry. It's okay. Oh, yeah. Congrats. I got you one too.
Oh, that's crazy. I'm scared of you.
Congrats.
Do I post
Oh.
And
show more presentation. The judges are still working on it, so we will give them a little bit. Oh wait, picture. I'm gonna take a picture. All right, guys, now time for the main prize. Who's excited? Woo! Okay, so the judges have thought long and hard and very, very long to decide who the best research presentation would be, and they have come to the consensus that the winner for the best research presentation is, drumroll please, none other than wrist bone fracture detection team. Please come up to the stage to get your medal. Guys, come on up. Y'all were the best team because you're wearing lab coats already. Like so appreciate. Congrats. These are all smaller than I thought they would be. Congrats. Oh, I got an extra one. All right, that concludes the end of the Spring 2023 Research Presentation Night. Thank you guys so much for coming. I would just like to give some final remarks before y'all leave. First off, thank you to the judges. We really appreciate y'all coming for us and judging these presentations for us. Thank you. Round of applause. And then thank you to the faculty advisors who were there to help our participants with their projects. Thank you to Stan for helping out with the pizza. And thank you to all the teams and all the leads. Y'all did great work. I'm super proud of every single one of y'all, the leads, and Pranav has a few words to say, so let's give it up for Pranav.
Hi, so this will actually be my last semester at ACM. But it's been a good experience so far. I joined 3 semesters ago as a participant, and Roman was my team lead. Actually, was there. So shout out to him. I was actually on the same team as CC. I remember being worried that I would not be a fit for my team when I started because I had no idea about machine learning or how to use the data set. But my team lead guided me, and I guess I'm grateful for that. And my team also helped me a lot, and we ended up winning. So that's why I decided to stay in ACM research. And it's been a great experience so far. I became a team lead because I wanted to continue lead my own project, and then I continued as a director so I could help CC with the whole organization, the division. And yeah, it's been a great experience, especially the build nights and the applications. That was a fun time. And ACM has definitely been one of the best parts of my college career at UTD. And I hope you guys join ACM Research if you're not on ACM. Thank you. Also, I have to go. I have a criminology paper due in 20 minutes, so I have to run.
Y'all can leave now. Thank you so much for coming. I can assure you next semester we'll definitely start a lot earlier than this.
That was awesome. All the projects were super impressive. I heard you really pushed it.
Yeah.
This is great. Good job, y'all.
Thank you. Thank you so much for coming.
Yeah, I'm excited. Okay, good luck.
Wait, Prof.
No, you need to finish your criminology thing. Okay. I don't know how.
Alessio, can you take a picture?